So now we start studying convexity as an application of this local study of the last theorem. And so the title of this section is Convexity. So let me say that convexity is an extremely important topic in the mathematical analysis, not only in the analysis one, not only when we are concerned with the study of a real function of real variable. Convexity is something which is really basic, really fundamental in the study of the variational calculus. I sometimes cite variational calculus, which is a very important branch of mathematical analysis. That means finding the state of minima of some so-called functionals are generalization of functions. So if you have a physical system, the energy of the physical system typically is a functional, and you want to know which are the physical configurations of the system that minimize the energy, because in general they are the configuration of stable equilibrium. Okay, so they are very important from the physical point of view. And convexity is a very, very important tool in order to establish this property of minimality. Okay, so it is very important. Nevertheless, in this course, we will treat convexity in a very elementary way. Okay. Also, the definition I will give is not the most general one, and the treatment will be really the minimum in order to be able to perform a study of function in a proper way. Okay, it is the minimum for us. If you want to deepen the idea of convexity, please go to the classics of the analysis. That can be the book of Apostol, for instance, or in Italian, the books by Prodi and Giusti. So, the definition I give you of convexity is the following. Let's start, as usual, with a function defined on an open interval AB. And consider a point x bar in this interval. Since the interval is open, x bar will be an internal point. So a point such that there is a neighborhood of this point which is contained in the interval. Moreover, suppose that f is differentiable at x bar. This means that the graph of the function f admits a tangent line at x bar, f of x bar. When I say that f is differentiable at x bar, I'm already giving the most generality up. Okay? If you go to the general treatise on mathematical analysis, this hypothesis is not included in the definition of convexity. But for our purposes, we can assume this hypothesis. It simplifies a lot the rest of our treatment. Now, the function f is said to be convex at the point x bar if there exists a neighborhood U of x bar such that for every x in this neighborhood U, we have f of x not smaller than the first polynomial of Taylor of the function f around the point x bar. So f of x bar plus f prime of x bar times x minus x bar. Okay? What does it mean? It means, so remember that this is the tangent line. To the graph of f at the point x bar, f of x bar. And this means that here in this neighborhood U of x bar, This means that if x bar is here, x bar f of x bar, so here we have the tangent line. So this is P1. This is f of x. The fact that f is larger than or equal to P1 in this neighborhood means that the graph of f lies above. The tangent line, P1. Notice that this has to be true in some neighborhood of x bar. So this is a local this is a local fact. Okay, this is true only locally. Okay, and this is the definition of convexity in a point. So very naturally we can move from the local convexity at a point to the convexity on an interval, and the generalization is standard, and now I guess you probably know how this generalization works. So if you have a function f from an interval, an open interval ab to R, which is differentiable in the whole interval AB, is said to be convex in the whole interval AB if f is convex at all points of AB. Okay, so this means the following. You have a function, and this is the graph of the function, which is convex at every point. That means that for every point you consider, the tangent line lies locally below the function. So at every point, the tangent line Okay, this is the basic definition of convexity, and there is also the counterpart of convexity, which is concavity. So this is our definition. Our definition says that if you have a function f differentiable, f from AB to R, which is differentiable at a certain point at x bar in AB, is said to be concave at the point x bar if the relationship that defines convexity is reversed, so f is not larger than the tangent at the point x bar, which is f of x bar plus f prime of x bar times x minus x bar. Okay? And as usual, the definition of concavity, not at a point, but in a whole interval, you have that f differentiable in AB is said to be concave in AB if f is concave at all points, at every point of AB. And now there is the basic theorem, which is really the theorem which is important for us, the only result that is important for us when talking about convexity, and it is the following theorem. You have a function f which is twice differentiable in all points of AB with the second derivative which is positive on AB, then f is convex, but I would add strictly convex, and then I will explain what is the meaning of this strictly. You can imagine, but I have to tell you clearly. Strictly convex in the whole interval AB. And now we go for the proof. Oh, sorry. First, let me remark. F is said to be strictly convex in an interval AB if for every x bar in AB there exists a neighborhood U of x bar such that f of x is strictly larger than f of x bar plus f prime of x bar x minus x bar. So as you probably already guessed, the inequality that defines convexity holds without equal, just a strict inequality here. So the same, of course, for strict concavity. This is strictly concave. So, and again, the proof. So, let x bar be an arbitrary point in AB. We know that f is twice differentiable at x bar and the second derivative is strictly positive, and we aim at proving that f is convex at x bar. Let us consider the function which is the distance between f and p1, g of x is equal to f of x minus p1 of x. This is f of x bar by definition of p1, f of x minus, by definition of p1, f of x bar minus f prime of x bar times x minus x bar. Notice that g of x bar is equal to 0, and g prime of x bar is equal to f prime of x bar minus f prime of x bar, which is equal to 0, 2. G second of x bar is equal to f second of x bar, which is a strictly positive quantity. Now, by the theorem on the relationship between derivatives and stationary points, we have that x bar is a strict minimum of the function g. This means that there exists a neighborhood u of x bar such that for every x in u minus x bar, g of x is strictly larger than g of x bar, which is equal to 0. This means that f of x, by definition of g, f of x minus p1 of x bar is positive, then f of x is larger than p1 of x bar for every x in u minus x bar, then f, by definition of convexity at x bar, f is convex at x bar. Now, since x bar is an arbitrary point in the interval, by the arbitrariness of x bar, we conclude that f is convex in the whole AB. Okay, and is strictly convex. So remember the definition. This is true, of course, for every x in U, not at x bar, because at x bar there is the equality. And a remark. So an analogous result holds for concavity we have that f second negative for every x in AB means that f is strictly concave at in the whole interval in AB. And this is what we will use. And so I want to stress this fact that pictorially the graph of a convex function is, let me say, happy. So he's smiling, because in order to remain always above the tangent at every point, the graph has to take a curvature, which is the curvature of a smile. One says also that the concavity is upwards. Okay? So, like in a smile. On the other hand, the graph of a concave function is sad. Yes, because in order to remain below the tangent at every point, so the concavity here is downwards, so it seems a sad mouth. Okay, so pictorially, this is exactly what was missing when we studied the function x e to the minus x. And so we will move forward to end up the study of this function, but before doing that I have to introduce another notion, which is the notion of inflection point. So the definition is the following: x, so we have a function f from ab to r, x bar in R, sorry, in AB. X bar is said to be an inflection point of the function f if the concavity of f changes at x bar. Namely, there exists a u, which is a right neighborhood of x bar, and v, which is a left neighborhood of x bar, such that f is concave in U and convex in V, or f is concave in V and convex in U. What happens? So the situation is the following. Try to, so pictorially, one has to draw a function which is smiling, for instance, here, or which is said here, and then it becomes happy, it becomes smiling. You see there is a point here where the function is not smiling nor sad. And what happens to the tangent here? Typically the tangent is below the function where the function is concave, and above the function here. So the tangent, so typically, the tangent crosses the graph in correspondence of an inflection point. So, of course, if f is twice differentiable in AB, and f second is continuous at x bar, then f second of x bar is equal to 0. And this is how we will single out the inflection point. So let us go to our example, our study of function. F of x equal to x e to the minus x. So the question is find the intervals of convexity, the intervals of concavity, and the inflection points. So as we already studied, we have that f second of x is equal to x minus 2 e to the minus x. And this is positive for x larger than 2, 0 for x equal to 2, and negative for x less than 2. So now we can use the theorem and conclude that f is concave in minus infinity to f is convex in 2 plus infinity. And of course, in 2 there is a change of concavity, so x equal to 2 is an inflection point. Of f. And now we can complete our study of function. Remember that we knew that there was a maximum at 1 here. Then the function went to 0, and here there is a point 2. And now the function is concave here, which means that the function, is said in this part of the graph, and is convex here after 2. And here there is an inflection point. Okay? And so from the point of view of why are we interested in inflection points? Are they useful or not? Now, the answer is that inflection points are extremely useful in the study of natural phenomena. If you remember when the pandemic of COVID-19 started last year in March, epidemiologists were studying the evolution of the curve of people who got sick. And at the beginning, there was an exponential growth. Everybody was extremely worried because the exponential is a very fast growing low. And at every day, they announced something like, we hope we are close to the inflection point, because when an exponential curve starts having a change of concavity, so an inflection point, it means that it ceases to be exponential. So the increase of the number of people that got sick was starting not to decline, but the growth of this number was starting to decline. And this was exactly the first signal that something was getting a bit better. And then when we had the second wave last autumn, the same reasoning was made. Okay, so inflection points are extremely useful in the study of natural phenomena because they signal when things are starting to change, and they give a time scale to the process. So let me write here something. COVID-19 pandemic. So we had here an exponential growth. In the exponential, there is no inflection point. But at some point, there was an inflection point here. So there is a first part, which is exponential growth. Then here there is an inflection point. And now after the inflection point, we were able to estimate the peak. And this was extremely important. And then there was the descent. Overall, this is a curve which is called a logistic curve. We will study this logistic curve in the next lecture on differential equation. Now I want just to stress the importance, the relevance of the inflection point. Okay? And this is almost all for today, except that I give you an exercise which is extremely funny and useful, which is the following. Write the Maclaurin polynomial P1000, so you go up to the power 1000 of x for the function f of x equal to the exponential of minus 1 over x squared for x different from 0, and 0 for x equal to 0. Okay? This is a very strange and funny exercise if you want to do that. And so you can do it by induction, but it is very difficult. My suggestion, try to write P1, P2, if you want P3, and then see what happens. So another exercise, which is useful for analysis 2, not only for analysis 1, is the following. So consider PM be this polynomial here, the sum of k from 0 to m of x to the x to the power k divided by k factorial. So that is the Maclaurin polynomial of degree m of the exponential e to the x. Okay? And now prove that for every x in R, the distance between the exponential and this Maclaurin polynomial goes to 0 as m goes to plus infinity. Okay? And so that one can write e to the x is equal to j from 0 up to infinity, x to j over j factorial, because the remainder is going to 0. Suggestion, use Maclaurin polynomial with the remainder in the form of Lagrange. Second, so you fix a quantity A larger than 0 and prove that there exists a AM that depends on A such that e to the x minus Pm of x is less than Am. So you will see the meaning of this exercise at analysis 2. Okay, now it is just an exercise, quite technical, but I suggest you to try to do that. Okay, and this is all for what concerns Taylor theory and differential calculus and all this construction, concavity and convexity and so on. And now we will change completely topics and we will go to differential equation. But before going to differential equation, I will give you some notion about complex numbers that are very important. So now the spirit of the course changes a bit and we go to application. Okay? So goodbye, see you next time.